In the previous videos and video lectures, we analyzed electrical circuits when there is a sinusoidal input source, like it can be voltage or current source, and we are interested in steady-state behavior of the output or any variable in the circuit. We introduced the concept of the phasor and how we can use this concept to transform differential equations and analyze the output behavior in a more simple algebraic manner. Today, I would like to talk about a very important concept, which is impedance. Okay, so the question is, if our goal is only to perform sinusoidal steady-state analysis, if you don't care the transients, what happens in between 0 to as the circuit reaches infinity, do we really need to derive the ordinary differential equation of the circuit first? It can be okay for a first order circuit. It can be even okay for a second order circuit. But when you go higher order circuits, deriving the ODE is really painful. And if you want like to, for example, analyze a different variable, you need to come up with a different equation anyway. Okay, the good thing is, no, we don't need to do that, because if you use the phasor notation and the concept of impedance, we can analyze circuits as if they're resistive circuits. Okay, what is the difference between resistive and circuits dynamic circuit? It's because in one case we have static algebraic equation, in the other case we need to deal with the differential equations. Okay, so what are we going to do is we use the concept of phasor domain to transform the circuit in a complex resistive looking like a circuit. It won't be resistive, but we will use called impedance. Okay, so let's remember, given a time domain sinusoid such as a times cosine omega t plus phase, which is a magnitude phase, we can convert it into phasor notation, which is a magnitude and phase, or we can write in this form. Okay, so, and we know that cosine omega t is 1 in phasor concept. So what is impedance? Before going to impedance, let's remember resistance. Resistance in time domain is very simple. We have a resistor, and you use the Ohm's law, such that the voltage across the resistor is equal to resistance, it's a constant, times its current. For all times, this is equal. Okay, so if we go to phasor domain, so let's assume that omega t is at like sinusoid, and of course it should be also sinusoid. We have the same relation, right? Because it's r is just a constant. Okay, so what is impedance? Impedance is generalization of resistance in the phasor domain. So what are we going to do is very simple. So we have an element. It can be resistor, capacitor, inductor, or maybe combination of them or something like that. So what are we going to do is, so it will have a voltage, and we will assume that it's in phasor form. So it should be in a sinusoid form. It can be cosine, sine, or phase shift version. The current also should satisfy this. Okay. So if we have a linear relationship in the phasor domain, we call this constant, which is a complex constant, impedance. So the idea is very simple. Instead of v of t is equal to r times I, where r is a real constant, now we have a complex constant. Okay, good. So let's look at resistors. Okay, in time domain we have this simple relationship. We have this phasor expression. We already know that. And impedance of a resistor is simply its resistance. Nothing changed. So let's look at capacitor, and let's remember capacitors time domain equation. C times V dot is equal to I. Okay, good. So we can transform V dot, the derivative, using the concept of phasor. We already know that, which is equal to C times J omega. V of J omega is equal to I J omega. So what is the impedance? The capacitance is equal to 1 over C omega J. Let's look at the result. It's true. Okay, so this is the impedance of the capacitor in phasor domain. So what are we going to do is, we will treat impedance as if it's resistance. In resistive circuits, we will do analysis using this value. Okay, good. So inductor, it's very similar. V is equal to L times I dot. V of J omega is equal to, this is even easier, J L omega I J omega, and this is equal to ZL, which is equal to J L omega. So let's check if it's correct. This is correct. As you can see, we have impedance of a resistor capacitor, and inductor, and these are the most important elements for our electrical circuits course in terms of energy storage elements. Okay, good. So let's solve an example to better understand how we can use this concept. Okay, so this is a circuit. It's given that R is equal to 1 ohm and we have a capacitor, two capacitors, equal capacitance, which is 1 farad. So input is given as cosine omega t. The frequency is 1 radian per second, and the goal is computing V naught or output voltage. So what are we going to do is we will first transform the circuit in phasor domain. So since cosine omega t is the base signal, this is simply equal to 1. This is just 1. Okay, so it doesn't have a phase. It has 1 ohm resistance. Since in the resistance, the impedance is equal to this resistance, this is equal to 1. This is equal to 1. So what is capacitance? The impedance of the capacitance is equal to 1 over C times J omega. Okay, omega is equal to 1, C equals to 1. So it's 1 over J omega, and we know that 1 over J omega is equal to minus C. So if we transform everything, we will obtain this. Okay, so this is minus J, and we will treat as if it's resistance in resistive circuits. Okay, nothing will be different. Okay, so it's complex. It may be non-intuitive for many of you, but computational, it's super convenient. Okay, so the goal is computing V naught J because it's in the phasor domain. So first, let's compute VA. This is VA. And again, since we are in phasor domain now, everything will be in phasors notation. Okay, so VA minus 1 divided by 1 plus VA divided by J plus VA divided by 1 minus J is equal to 0. That's it. Okay, so we are doing classical node voltage analysis. The only problem is we have negative and even, as you can see, complex resistances. So VA, that's good, 1 plus not 1 over J. 1 over J is equal to minus J. We know that. That's good. No, it's actually it's minus J, so it will be plus J. That's great. Plus 1 over 1 minus J is equal to 0. That's great. So we are going somewhere from here. Okay, so VA is equal to, that's great, 1 plus J. So if I multiply here with its complex conjugate, I will obtain that it's equal to 1 plus J divided by 2, which is equal to 0. That's great. So this is equal to VA 3 over 2 plus 3 over 2 J, it's equal to 0. So we are close to computing VA. So VA is equal to 2 over 3. Okay. No, okay, 2 over 3, sorry for that. 2 over 3. Okay, I know that. 1 over 1 plus J. I will keep it like that. I can convert 1 over 1 plus J easily, but I will just keep it like that because I want to compute V naught. Okay, so as you can see, VA is a complex number. It is a magnet, it's phase, so we can compute VA with respect to the base signal, which is cosine omega t. But our goal is output voltage. Let's concentrate on that. Okay, that's good. So let's clean this part. So what is V naught? V naught is the voltage here, okay? And we know VA, so it acts like a complex voltage divider. So VO is equal to VA divided by 1 minus J times minus J. Okay, so let's change the color. So that's it, right? This is the total impedance. This is the impedance of V naught, and that's it. So VO is equal to 2 over 3. That's great. Minus J, 1 minus J, 1 plus J. Okay, as you can see, these are complex conjugate of each other. So V naught is equal to 1 over 3. This is 2, it's minus J. Okay, that's good. So what's the magnitude? What's the phase? Obviously, magnitude is equal to 1 over 3. So what is the phase? Phase of V naught is equal to, so 1 over 3 doesn't have a phase, it is minus j, and we know that minus j is equal to minus pi over 2, or it's equal to minus 90 degrees. So I know the magnitude, I know the phase. So I can convert it to time domain, which is very easy. So technically VOT is equal to 1 over 3 cosine omega t minus pi over 2, or if you like, you can use degrees. Okay, let's look at the result. It should be correct. As you can see, it's correct. Okay, as you can see, the only complexity here is doing some sort of complex algebra. But in my opinion, doing complex algebra is much easier than solving differential equations, dealing with derivatives and integrators and initial conditions.